Okay, well, good morning, everyone. We're back. My name is André Tétreault, and I'm Director of the Test and Diagnostics Department here at VibroSystM. As usual, I'm joined with my colleague, Paul Amelinckx. Paul is one of our analysts here at the Test and Diagnostics Department. He'll be handling, as usual, the logistics of what you see on the screen, and also he'll be handling any and all questions either in Spanish or in Portuguese. So, buenos dias, Paul, or should I say bon dia, Paul?
Buenos dias, bon dia. Thank you, André. Hello, everyone. And if there's any glitch in the transmission, it will be my fault.
That's correct.
For our friends in Latin America and Brazil, please feel free to submit your questions in Spanish or Portuguese. We'll be glad to answer them as well. Para nuestros amigos de América Latina y Brasil, ustedes bien pueden formular sus preguntas en español o portugués, las que responderemos con mucho gusto.
So good morning and welcome to our 7th Q&A session live on YouTube, directly from our head offices here in beautiful Montreal, Quebec, Canada. I'm very happy to be here this morning to discuss, among other things, hydro generators and especially pole face or rotor pole joint temperature. We have a slightly different format for you today, although we receive and have received many questions following previous Q&A sessions. There's one question that comes up quite frequently and we've never actually answered because simply the question requires a more detailed, more developed answer. Therefore, today we're going to answer that question, and that question is, what would you recommend as the optimum cost return on our investment system for our generators? So we have a video for you this morning, which we'll look at very shortly. And it's basically a rundown of the standard system that we would recommend for a hydro generator with a power output less than, a power output at 100 megawatts or more. And then we have, I prepared for you a PowerPoint slide listing all the different equipment, what it looks like installed, how many, and so forth, and some of the results that it can provide. And then I have a series of videos for you, short videos, explaining basically based on this or that equipment, what type of phenomena can we look at or analyze or detect based on the rotor, based on the stator, based on air gap, based on flux, based on acceleration, and of course temperature. And we will follow up on that with some short videos and slides on rotor pole face or rotor pole joints overheating. Now, of course, during this, during the morning, if you have any questions, Paul will make it his mission in life to transmit those questions to me. So remember, if you want to ask questions, you do need to log on to your YouTube account. So.
Yep. Remember that to be able to submit your questions during the Q&A session, you need to log on to your YouTube account. As mentioned in previous Q&A sessions, we still want to make sure that all questions are asked previously are answered. But today we will answer them. We will answer the remaining questions at the end of the session if we have time. Recuerde que para poder enviar sus preguntas durante la sesión de preguntas y respuestas, usted necesita ingresar con su cuenta de YouTube. Tal como hemos mencionado en anteriores oportunidades, nuestro objetivo es que todas sus preguntas del día sean respondidas durante la sesión. Sin embargo, el día de hoy responderemos todas las preguntas al final de la sesión si tenemos tiempo.
Very good. So today, as I mentioned, the subject is hydro generators, especially those at 100 megawatts or more. We will do the same type of presentation for the turbo market in our next Q&A session. So we'll cover all the similar details as to what we recommend for turbo generators. And the next Q&A session will be held on December 10th. So make sure you put that date in your calendar so that you can watch that Q&A session on turbo generators. So, without further ado, let's start our first video. I will make some comments, so I will regularly stop it, interrupt it, and put some comments to it, because it's basically a video with no sound. It's just a rundown of the equipment. So
let me
Yep.
transfer to you the control, just
Okay.
a sec. There you go.
Okay, so I'll start the video. Okay, so this is basically a system we recommend for generators that have 100 megawatts or more. Now, first thing we do is kind of strange, but we specify a synchronization probe, which is probably the smallest piece of equipment in the system. And the reason for that is that for hydro generators, everything that we measure on the unit, whether it's acceleration, heat, vibration, air gap, flux, axial displacement, whatever we measure, everything is correlated with the rotation of the unit and the number of poles, so that all the information is easily correlated. So the first thing we need is a synchronization probe to give us a signal telling us exactly where we are, how the rotor is positioned when we take readings. For pump storage units, which rotate in both directions, well, you do need two to give you the proper position in both directions. So the first thing that we need is a synchronization probe, and that probe usually, and this is strongly recommended, is installed in the turbine pit. The reason for that is that if you do need to make some adjustments, it's very easy to go there and make those adjustments without having to dewater the unit and have all the locks and everything and the security process in play. So the best place to position that is in the turbine pit. Okay, I have an example here. And then what we recommend is shaft displacement probes, either 4 or 6. It says 6 here, which is the maximum number of sensors for hydro generators. 2 are installed in the XY format position in the turbine guide bearing. 2 are installed at the lower guide just below the rotor, and then 2 are installed at the upper guide bearing for units that are not umbrella type units and do have an upper guide bearing. Okay, so we have a total of 6. We have an example here, picture. These are capacitive probes. We'll get into that in the slide part of the presentation. Now, in some cases, it's important to be able to monitor the axial displacement of the unit. I'll show you an example. We have a small video on that, and it's important in some cases to measure the axial displacement to protect basically the thrust guide bearing. In some cases, you have thrust guide bearing wipeouts, and people wonder why that is, and sometimes that little probe will tell you exactly what the problem is. Okay, so we'll take a look at that as well. Okay, here we have an example of a air gap sensor. This is one type. We have a few different types depending on the gap, depending on the location, I guess. We usually recommend 12 in this setup. We recommend 12, 8 at the top and 4 at the bottom. Now, I was asked the question, why 4 at the bottom? Well, usually budgetary concerns are always an issue, of course, and the number of input modules that we have with this system is limited, so we have to make some choices. And the best scenario would be 8 on top, 8 at the bottom, but in cases where that's not possible, we recommend to put 8 at the top instead of 4 at the bottom, because in most cases, the stator frame and core are more flexible at the top. There's less support than at the bottom. At the bottom, with the sole plates and gravity, they are less susceptible to distortions or deviations. That doesn't mean that they don't occur, but they're less susceptible to those. So the top is definitely the most susceptible to having serious distortions. So with the 8 on the top and the 4 at the bottom, you can at least analyze the thermal behavior as the unit expands with heat, and then it contracts when it gets colder, and it gives you the best possible coverage, I guess, for rotor and stator shape. Okay, an example of a sensor installed here. And then in some cases, if you want to measure the situation in regards to excitation provided by the rotor, the magnetic flux which is generated by each pole, There's a magnetic flux probe that is installed also on the core next to a air gap sensor, and that is used to see if there's any shorted turn issues on any or many of the poles of your rotor. Okay, an example here installed. And then we recommend 6 fiber optic accelerometers for absolute vibration monitoring of the end windings. In many cases, when I mention this, people say, well, isn't that basically a turbo generator issue? And although it is quite frequently or more frequently a problem with turbo generators because of the length of the end windings and there's least support. I mean, they can go out 2 meters and there's not much support, so the vibration, the energy, gravity, and all that can cause issues. But that doesn't mean that there isn't issues on hydro generators. And there's actually a paper I co-wrote with some Rio Tinto Alcan engineers where they had serious issues with their units, and the fiber optic accelerometers were very instrumental in showing what the problems were. So we recommend installing 6 on the end windings. And we also recommend putting 6 stator bar vibration probes. These are capacitive probes. They're installed on the wedges, looking towards the bar, looking towards stator bar to see how tight the wedging system is, how tight are the bars in the slots, because as you know, epoxy mica hates to rub against anything, and it creates wear and tear of the insulation, so you want the vibration to be as little as possible. So those types of sensors are able to monitor that and tell you if there's an issue. So you have an FOA, which is installed on the cap, and you'll have a stator bar vibration sensor looking at the bar inside the slot. Next, we have accelerometers, piezoelectric in this case, that are used to monitor the vibration, the absolute vibration, or the acceleration of the core and of the frame. So we install 4, in this case here, 4 on the frame, and we'll install 4 more on the core. And the reason for that is we want to see not only how much the core and the frame are vibrating, but we would like to see whether they're vibrating in sync. Are they moving together, or is there a lag telling us that there's a looseness that is developing between the core and the frame? Because if that's the case, you'll start having some arcing, potentially some arcing between the core and the frame, causing severe damage. We've had quite a few cases of those. So we use those in sync to see if there's any kind of looseness. And we also install some on the pressure plates. The reason for that is the pressure plates are there to, with the compression bolt, are there to make sure that the laminations are stacked correctly and tightly and remain tight. You cannot have laminations that come loose, because if they come loose, they start rubbing against each other, and then the insulation will wear out, and then you'll have some contact between 2 laminations, creating eddy currents, causing overheating, causing all kinds of issues. And historically, this combination of pressure plates and compression bolts are usually neglected. The maintenance is not done on those, and they become loose, and everybody wonders why the core is overheating. Well, in many cases, that's why. So it's important to monitor that and be able to see if those are coming loose. Now, there's also, let me just move that back here. We also install temperature sensors to be able to see if we have some temperature issues, either caused by the laminations overheating or caused by the stator bars overheating. So we will put 3 serial lines of ThermaWatch stator sensors. Usually there's a maximum of 100 per line. And we'll install 1 line on the stator bars to see if the bars are overheating. And we will install 2 on the stator core to see if the core is overheating. Okay, so that gives you temperature coverage. And finally, we will put some ThermaWatch rotor sensors, infrared sensors that are looking towards the rotor through the ventilation holes, and are able to tell us if we have temperature issues with the poles while the unit is in operation. I have an example here. Okay, so for hydro generators, that's basically the recommended system. We have Zoom cabinets with electronics and corresponding software that can communicate with our equipment, retrieve all the data, can send the data to your SCADA system. We can also get information from your SCADA system into our system, making it a fully integrated system. Okay, so that was our first video. Now, the following slides will, I guess, emphasize or detail what we've just seen as a video, and looking at different particular details into more detail. And at some point I'll stop and I'll show you some videos that will support what I'm trying to emphasize here. So let's move ahead. One of the technologies we use, of course, is the capacitive displacement probes. The technology that is used for these probes is the same as what we use for the air gap sensors, in that we create an electrical field instead of a magnetic field. So these are not inductive probes, these are capacitive probes. And the beauty of those probes is that since we create an electrical field, that the surface material is inconsequential. It doesn't really matter what type of material is present. It doesn't matter if it's copper, brass, titanium, steel, carbon steel, iron, rust. It doesn't really matter. So long as it's conductive or semiconductive, the performance is the same. So the electrical field that is created creates a certain amount of current depending on the distance. Without going into all the physical details, we create a capacitor, and all the parameters are controlled with the exception of the distance. So any variation in the amount of current that flows through can only be attributed to a variation in distance. Okay, so we have a picture here. Of course, sensors are installed at 90 degrees interval so that you're able to correlate the movement of the shaft in two directions. And that's very useful when you want to produce orbit graphs. And the orbit graphs are produced based on the information to two sensors, and you can still see the key phaser here, and we can see the two probes are here, 90-degree intervals, and they're monitoring the movement of the shaft as the shaft rotates. And with this information, it's able to produce this type of graph, which all the mechanical engineers understand, and that's basically the process of the shaft, its position, while it's rotating. So what you have on the screen is multiple rotations, and it is during a startup of a hydro generator, and we can see that prior to excitation the unit is rotating in this position, and as the field is introduced the unit moves over to this direction and then rotates over. So it adopts a center in this location as opposed to this. So this is what we call mechanical center, and this is the electromagnetic center. So this tells me immediately that the air gap is uneven. We see that consistently when we analyze data, correct, Paul?
Yeah.
And this is easy for us to analyze. It means that the air gap is smaller in this area here prior to excitation, and when they excite, the magnetic pull is stronger there. Therefore, the unit will go in that direction. It will remain there so long as the magnetic field is present. Once the magnetic field is removed, the unit will immediately go back to its mechanical center. Now, inductive technology is used for displacement application as well, mostly where capacitive technology is not compatible. For example, inductive technology is sometimes used for axial displacement because of the much larger gaps to cover. It's difficult for a capacitive probe to go 15, 20 millimeters, where an inductive probe can provide significant precision for you to do that. So I have an example here. We have a sensor here, okay, and it's looking at the axial movement of this unit. In fact, this case here is one of the cases I used during my training courses to show why axial displacement monitoring is important. This unit had a thrust guide bearing wipeout, and they made a whole list of repairs, not only to the thrust guide bearing, but they also made some modifications to the turbine and so forth. And when they put the unit back online, within a month the unit failed again, and this little sensor provided the information they required to be able to determine what the issue was. So we'll see that also in some videos. In regards to air gap, as I mentioned, there's a few models. It all depends on the size of the air gap. The one on the left is very small size. It's like from 1 to 10 millimeters. The second one is from 2 to 20 or 2 to 25 millimeters. The third is from 5 to 50, and the one on the right is, depending on the conditioner, it's 5 to 50 or 5 to 35, if I remember correctly. They're flat sensors mounted on the stator wall, and it is patented technology. So we have some examples here of sensors which are installed. One of the questions we get quite frequently is, do you need to remove poles or remove the entire rotor to install the sensors? And the answer is no and no. I've installed quite a few when I was in tech support, and although when the rotor's in place it's physically more difficult because you're in a cramped space, it's not comfortable, it's usually hot, it's difficult. However, in my case, I preferred that setup because the sensors have to be installed in a very specific position. For example, you see a position here where the sensor is between poles. If you have 8 sensors, all 8 must be in this exact same position. If the sensor is between poles, the other 7 have to be in between poles as well. And although having the rotor in place is very uncomfortable, when you glue them on, you can see that you're in the correct position because you're using the rotor as a reference, okay? So for me, it helped me sleep at night instead of having the rotor on the assembly floor and then just getting access to the stator and calculating all the different positions and hoping I didn't make a math mistake, okay? So you never need to remove a pole or remove the rotor to install air gap sensors, okay? So this is an example of a reading for 1 rotation from 8 air gap sensors. And in our training courses, we explain why this is, what this graph means and why this is important. And one thing you notice, they're all parallel, and we explain on the training course why that is. Here we have the same reading from 1 rotation can also produce a polar graph. So we can see the shape of the rotor and the shape of the stator and also their positions, one compared to the other. And as I mentioned, you can see in cases where the air gap is too small on one side, when you excite the unit will go into that direction. And you can see this type of information very easily with 1 measurement of the unit, and you can see the interactions between the rotor and the stator shapes and or positions. Okay. So air gap monitoring of hydro generators gives you a snapshot view of the rotor inside the stator while the machine generates power. So it replaces the need to take all these static readings that you know, historically people have been taking for years and years, and although in some cases the readings are very, very precise, basically what it tells you is what the shape and the position of the rotor and stator are when the unit is stopped and cold. It doesn't produce a lot of power there. You're not really interested in your oil temperature for your car while it's in the driveway. You're interested what the oil temperature is when you're on the highway. It's the same for us in this case. When you want to see what the rotor shape and stator shapes are when the unit's in operation where it's generating power. This is an example of an air gap sensor looking at what happens to the air gap when the rotor is energized. And you can see there's a noticeable decrease in air gap, and that is usually caused by the sudden expansion of the rotor and the sudden contraction of the stator. So the movement of both create this decrease in air gap. Okay. So before I move on to the magnetic flux probe, I want to show you a small video showing you some of the issues that we have when we look at the rotor with air gap probes. We have the rim expansion anomalies, the circularity anomalies, stiffness anomalies, concentricity anomalies, pole radial position anomalies. These are all parameters that we look at when we analyze the rotors. What is required to identify these phenomena? Well, shaft displacement probes is always very important to see how much the rotor is moving You need the air gap probes to be able to tell what the rotor shapes and positions are. The synchronization probe to tell us where we are, where the poles are. And in some cases, there's additional equipment to help identify the root cause, such as magnetic flux probes, core vibration accelerometers, and so forth. The shaft displacement probes, as mentioned before, there's 2 on the turbine guide bearing, 2 on the lower guide bearing, and if there's an upper guide bearing, 2 on the upper guide bearing as well. I have an example here. Okay, so what are the different phenomena that we can tell? Let's just speed this up a little bit here. Okay, if we look at the rotor. First and foremost, rim expansion anomalies. Now these represent an analysis of the rotor rim based on the behavior of each pole in regards to different machine operating conditions, from slow roll, very slow speed, to 100% power with the temperature stabilized. Okay, so if we look at the rotor shape, if the unit is cold, let's say it's perfectly round, and as you increase the speed or as you increase the load, you will see rim distortions. And rim distortions are usually represented by not one pole sticking out, but you can see an entire section is actually coming off. Maybe not coming off, but is moving outwards at a greater rate than anywhere else. Okay, that's the type of analysis that you can perform with the air gap sensor. And it's quite common, by the way. I don't want to frighten anybody, but it's quite common.
Yeah.
Circularity anomalies, well, these represent the difference between the maximum and the minimum radii from the rotor best center. Okay, so in this case, we have the initial rotor state, and eventually we'll have distortions, but at different locations, not just one location, but different locations. And that looks like a real rotor. Maybe surprisingly to some, but that looks like a real rotor. So the increase in circularity is caused by rotor shape distortion. The idea is to find out how much distortion and is it acceptable. Now the stiffness anomaly analysis, it represents the rotor circularity variation in regards to different machine operating conditions caused by the temperature variation effects, the magnetic force effects, load effects, and centrifugal force effects. So again, we look at distortions, but contrary to the circularity issue, circularity is basically looking at the same condition through time and see if that circularity changed. For example, if you look at the circularity at full load hot in January, what does it look like in April? What does it look like in July? Whereas the stiffness, we're looking at how does the rotor change or perform going through all the different conditions from cold all the way to full load hot. And again, in some cases, we can spot some significant distortions that need to be addressed. Concentricity anomalies represents an analysis of the rotor vectors at various machine operating conditions. Okay, so if the unit's cold and it's very centered, and then as it operates, it will start moving around, and the center won't stay in place. That center is based on not only its position, but also the rotor shape, because the center is based on the shape of the rotor. So if the rotor shape changes, its center is going to change. Pole radial position anomalies, that represents an analysis of each rotor pole over time at normal operating conditions. Okay, so in this case, we'll look at individual poles and see if their radial position is beyond a certain guideline from one pole to an adjacent pole and so forth. It's quite rare to see a pole sticking out a lot, but it is quite common to see poles that are sticking out more than they should, and that usually requires some action to be taken to fix that before it becomes loose and actually hits the stator. Okay, so that was the video on the rotor, and I want to show you the same concept with the stator. Again, things that we look at from the perspective of a stator. Again, circularity, stiffness, concentricity, but from the perspective of the stator. The equipment that is required, we can skip that because it's basically the same equipment that we use to look at the rotor, but now we're looking at the stator. Okay, so all the same equipment. So, circularity anomalies from the perspective of the stator. Well, it represents, again, the difference between the maximum and the minimum radii from the best center. Okay, so you have an initial stator state, which is perfectly round, and as you heat it up, as you excite the rotor, as you synchronize the unit, you introduce a whole bunch of forces, and that can, and usually does, influence greatly the actual end result of the stator shape. Stiffness anomalies represents the stator circularity variation in regards to different operating conditions caused, again, by temperature variations, magnetic force, and load effects. So again, initial stator state, which is round, and it will start deviating. It expands, and it can deviate because of these different forces. You can see sometimes a certain load, you'll start seeing some creeping, and distortions will appear, telling you that the expansion is not symmetrical, and you need to check sole plates, you need to check core to frame attachments, different components that need to be verified. Concentricity is also an analysis of the vectors, but in this case it's for the stator. Again, the stator, the vectors, the stator center is based on its shape and also its position. If the shape changes, the center will change, and obviously the vectors will change as well. Question is it a problem or is it within acceptable tolerances? All right, so that was the video I wanted to show you for this particular phenomena for the rotor and stator based on the hydro specification. Now, I want to show you a specific case that we looked at many years ago. It was in North America, and it was a brand new unit. And we were involved in monitoring the performance of this unit. This is not a real representation of the power station. It's just a general representation of a power station. As I said, a complete rotor and stator replacement was performed, and we were on site to take some readings and analyze the results. And I just wanted to show you what we were able to see. There was quite a lot going on. And the customer was very happy to have all this information so that he could have discussions with the manufacturer and try to get these problems resolved. So this unit had a system installed in 2011, was equipped with a zoom system included measuring air gap, relative shaft displacement, radial and axial. So we can see that 8 air gap sensors were installed at the upper part of the unit. And they had radial displacement probes at the lower guide bearing and 2 more at the turbine guide bearing, and they had an axial probe as well. And our famous synchronization probe. Okay, so we did all kinds of testing, including a startup, a field flash, and I wanted to show you the readings, the results that we were able to observe. And first, let's look at the rotor. Although the unit seemed to be operating normally, and this was our first graph with the unit at full speed. Of course, what I'm going to show you, of course, is a graphical or visual exaggeration, but still, it just shows you the distortions which were observed. Our data was able to show there were issues with this rotor. And the issue showed up when they synchronized, which, I'll stop the video here. Usually when we look at units, hydro generators, we will see distortions from the rotor perspective based on centrifugal forces. Therefore, as the unit increases in speed, we'll see the unit distort somewhat in some cases. And then probably the most dramatic one is when we apply the field. When the rotor is energized, that usually puts a lot of stress on the rotor and on the stator as well, but you will see some discrepancies show up. Usually when we synchronize, there's not much going on. In some cases, we wonder whether we actually missed the synchronization, or it has no impact whatsoever. And this was one of the first cases where we could see a significant impact, not when the unit was excited, but when they synchronized to the grid. So when they introduced very strong opposing forces to what the rotor was providing, coming from the stator, it had a significant impact. And let me just show you, if you look at the rotor poles all the way around, you'll notice that when they synchronized, there was a serious issue. Okay? So you can see not only did the poles come out, but the rotor actually shifted position. I had never seen that before. And this is a slow representation. You can see how the rotor shape changed significantly and actually moved downstream. Okay, so if I go back to the original rotor was, sorry, I'm trying to capture the 10.15, 11.22, circularity 11.96. This is during the same measurement, 13.02, 14.43, during the same measurement. So introducing the field coming from the core caused serious distortions to the rotor, and in fact pulled it towards downstream a bit. And as you can see, as they increased the load, the unit slowly pulled towards downstream. Okay? So that same rotor, as they increased the load, was slowly being pulled downstream. This is a brand new unit. This is totally unacceptable. And when they did the load rejection, two things happened. Not only does the rotor go back to its original position, because during the load rejection, in this case, the field's removed, but look at the rotor shape now. It's fantastic.
Quite the opposite as we would expect.
So it's really ugly, but when they remove the field and the unit goes into overspeed, it's fantastic. So it means that so long as the unit is producing power, this unit is in really bad shape. But if you stop it or if you remove the field, it looks fantastic. But the problem is that without any field, it doesn't produce a lot of power.
Yeah.
Okay, so it doesn't produce a lot of money. So you're not really interested in what the shape is when the unit's not producing any money. You're interested in what the shape is and the performance is when the unit is actually producing power. I had seen issues with low rejection measurements before, but synchronization effects, I had never seen that before. Okay, so that was from the perspective of the rotor. Obviously, there was some discussion between the utility and the manufacturer. And I want to show you what happened to the stator during those same measurements. Okay, so again, the unit seemed to be normal. And Zoom triggered some alarms, and we could see the stator circularity was very high. So again, we're going to exaggerate the phenomena just to emphasize the shape so you can see the distortion. Okay, so look at the encroachment of the stator even before synchronization. It was already, you can see it was already encroaching before they synchronized. And once they synchronized, the stator moved inwards at 270 degrees significantly. Okay, so you can see stator circularity initially is not so bad, but as they synchronized, stator circularity increased significantly. And I mean significantly. Okay, the stator circularity reaches critical tolerance levels when the unit's full load hot. Okay, so needless to say, the results were disappointing. The utility had to have serious discussions with the OEM to try to fix these issues. And as it says here, and I've seen this quite a few times, people will usually, if the vibration is low, people will usually tolerate a stator that's out of shape, saying to themselves, well, we'll fix it in a year or two. Just put the unit back online and let's produce power. And that's a mistake, because if the unit runs for a certain amount of time with a oval or a distorted shape, you can forget trying to fix that a few years later. It's not going to happen. The stator will adopt a permanent distorted shape, and corrective measures are just not going to fix the issue. So if you have a new unit and you have this problem, you need to fix that immediately and not wait a year or two and fix it down the line. Okay, can you put the presentation back on? Because I don't have it on my screen.
Okay, just a sec.
Just click on it so it goes back.
There you go.
Okay, thank you. So if we go back to where we were, magnetic flux. Now, in some cases, you may have some issues with shorted turns. It's a much greater issue on turbo generators, and in fact, they don't measure exactly the same thing. In turbo generators, they monitor the stray flux. They want to see the leakage flux coming off of each individual coil to see if there's any shorted turns. And the reason why it's maybe a little more important on turbo generators is that if you do have a certain amount of shorted turns, it causes a thermal imbalance, what they call a thermal sensitivity factor on the rotors. And at 3600 RPM, you can't afford to have heat issues on the rotor, because it will slightly distort its shape, and it's going to call what they call a rotor bowing. It bends. And at 3600 RPM, you can imagine the type of vibration that creates. So they cannot afford to have shorted turns, a significant amount of shorted turns on turbo generators, although most units have shorted turns. Turbo generators, hydro generators, there's usually some shorted turn issue on them, but it's usually not a factor, so you don't need to do anything about it. It's not a factor. However, you can have serious issues with shorted turns, and we have this sensor as a solution, and we put it next to an air gap sensor because the correlation between the two will tell us if there's a shorted turn or not. For example, you see the air gap profile here of that adjacent air gap sensor, and you can see that the magnetic flux is inversely proportional. So the smaller the air gap, the higher the magnetic field intensity. The larger the air gap, the lower the magnetic field intensity. And if you have any serious dip in the magnetic profile that is not corroborated by a greater air gap, then it means you have a shorted turn issue on that pole. Otherwise, they should all basically match. You can see how this shape is inversely proportional to this. So both sensors will tell you if you have shorted turn issues, and if you do, we will tell you which pole it is, and you can go in there and fix that issue at the next important outage. Now, I mentioned that end winding vibration is usually or more commonly used on turbo generators, but it is more used on hydro generators, and in fact, it's also used on large motors, on big sag mills and ball mills, because they also have end windings. They also have epoxy mica insulation, which does not like to vibrate. So it is important in some cases, especially if you suspect you have an issue with end winding vibration, which is turns up as loose ties, missing support blocks, dusting, greasing, cracking. Any of those are an indication that you have a vibration issue. And since it's high voltage, you cannot put a piezoelectric accelerometer, or you shouldn't do it. And fiber optic sensors are available. The ones you have on the screen is able to measure in 2 axes, so you can put it on an end cap and you can measure radial and tangential, or you can measure radial or axial. And these are very, very precise. As I mentioned before, this is a picture of the case study, the paper I wrote with the Rio Tinto Alcan guys, where they had issues with their hydro generator power station that was built in the 40s to produce aluminum for the war effort. Was one of the, if not the biggest power plant at that time, hydro plant. And they had all kinds of issues, and they used a whole list of fiber optic sensors to try to get a handle on why they were having so much issues on this one unit. Okay, so these are all pictures. Okay, of course the installation is not finished here. When the installation is finished, there's no tie wraps. These are actually covered with resin impregnated tape. So by the end, you can't even see the sensor. That's why I use these pictures, because you actually see the sensor, but when the installation is finished, you can't see a thing. All you see is tape. And that will give you the vibration of this winding in the radial direction and in the tangential direction. For the SBV sensors, you have a sensor here. Well, in fact, the sensor is here. This is a support, because we need to get it close enough to the bar, which is mounted on, the sensor is actually mounted on a plate here, and the ripple springs and the wedges are removed here, and our sensor is able to measure the gap from the sensor to the insulation, and we're able to monitor how much vibration occurs at that location on that bar. Okay, so we have a picture of 2 different models here. One on the left is a standard looking at the bar through the wedge, and not through the wedge, but the wedge is removed, but through the slot. And the other one is for those who do not want to remove wedges or slots or ripple springs. You can monitor the vibration of the bar just as it exits the core. Now for accelerometers, to measure the housing, the core, piezoelectric is fine. You don't need to have fiber optic because there's no significant amount of flux there. So the use of piezoelectric is fine. We have a picture here of a sensor looking at the housing. And here we have a picture of an accelerometer looking at the core. Now for temperature, RTDs are fine, but they're notoriously susceptible to defects because basically they're installed in a very harsh environment. And for those who would still like to be able to monitor the stator bar, the stator core, the press fingers, well, any location associated with the core, the bars, you can use these, what we call a ThermaWatch stator sensors, the digital sensors that provide their own temperature, so you can monitor the temperature of the core. On the left, don't get excited, that's not the price, that's just to give you an indication of the size. And it's a multi-point sensor line. As I said, you can go up to 100 sensors and you can install it just about everywhere. And it's digital, so there's no calibration, there's no adjustment. You just hook it up to the interface and you can measure the temperature as the unit operates. You have some examples here on stator windings and on press fingers. And it gives you this type of graphic, 1 per sensor. And you can monitor stator core temperature as well, same type of sensor, different location, and you can get an interpolation of the entire stator core, give you an indication if you have hot spots. This is real data here where you can see that the bottom part of the stator was much warmer than the upper part. Now for poles, and I'll skip this very quickly because I want to show you the little video before we finish today. This is a in fact, what you're seeing here is not the sensor per se, is the support that prevents the sensor from creeping inwards and actually touching the pole. The sensor is actually the center part here. Okay, everything else is just fixed in place, glued there to prevent the sensor from slowly over time creeping inwards and then actually hitting one of the poles. So we have an example here in Eastern Canada where you can see that three sensors were installed. This unit had been uprated, and that's one of the probably the most popular uses for this technology is for units that have replaced the turbine and I've increased the power output anywhere from 2 to 5 to 6, 7%, increasing the electromagnetic stress in the air gap, and the poles will overheat. Well, they will heat more. They will be subjected to more heat. The question is how much, and is it too much? And these sensors can tell you if that's the case. Okay, so more pictures here of the bracket with the probe inside. And also what you can do is look at pole joints. Pole joints, especially the flexible ones, as you can see on the right here. The flexible ones, of course, if the unit is cycled a lot, so the unit will expand, contract, expand, contract, expand, contract, and these are susceptible to cracks and eventually fail. And you can see the entire pole joint was vaporized. And you, in some cases, the flexible, these are much better, but as you can see, they're still susceptible to some damage. You can see one lamination has actually come off, and eventually this can fail. And in this case here, we could see that the pole was so hot, there's actually some blistering occurring. At the bottom, you can see where the paint's coming off. So it was so hot, and actually the paint's coming off the pole. Okay. And you have an indication here of, in red, the air gap is showing you the pole shapes, and in green, you can see the temperature that is measured by the probe. All right, so let me show you a small video I wanted to show you about the ThermaWatch rotor. Okay, you can see two types of connections. Of course, there are different models, but there's two standard types, the rigid or the flexible. And again, repeated cycling, centrifugal forces, heating, expansion, contraction can lead to failure of these interconnections. And it might be a better idea to be able to measure the temperature and detect hot rotor pole joints and replace them before they fail and cause damage, rather than instead of doing during an outage, just replacing it and preventing damage to the unit per se. Okay, so we have this last presentation for pole overheating. Okay, so to be able to monitor that, you need, of course, at least one ThermaWatch rotor. We recommend 3, but you need at least one. You need air gap to give you a reference to which poles are which. So it's nice to detect a pole that's overheating, but which one is it? So with the synchronization probe and the air gap sensors, you're able to identify. And by the way, before I forget, we've done testing on a few units like this, and so far, the hotter poles are always the ones that are closest to the stator.
Yeah.
Okay, the stress is hotter there, is higher, and so far we've been able to confirm any pole that is closer is usually hotter, in some cases much hotter. Measuring the flux also can be important to be able to see if the flux is more or less an issue. You have a picture here of the ThermaWatch rotor installed. Okay, so 3 gives you an indication of different locations on the rotor, looking at either the pole face or the pole joints. Okay, so in this case, you can detect hot spots on the pole faces or on the pole joints, giving you a chance to go in and see what's going on. You can detect, again, pole face temperature issues, rotor pole joints issues. You can also see a mortise bar overheating. There's an issue there. It will heat up, and you will be able to detect it with these sensors. Okay, so that pretty much covers the basic system that we recommend. Now, some other questions that arise quite often is questions about our ZOOMWatch platform, and that also is a very complex question. So we've decided to cover that issue in a future Q&A session. In fact, it's going to be on the session that will be held on January 21st. So make sure you also put that date in your calendar so that you can get information on the ZOOMWatch platform. And for those who want to play around with it before we get to January 21st, you can go on your search engine and just find out ZOOMWatch. And you can see here.
Let me, excuse me, Andre,
Yeah.
and let me publish your screen, just a sec.
Okay,
Yep.
sorry.
There you go.
Log on and see all the units that you're monitoring, and you can click on any unit and see what the performance is. You have a operability level that is calculated for the rotor, operability level for the stator, and an operability level for the shaft and bearings. If you click on any of these, it will give you a trend over time, so you can see if there's any evolution in regards to the operability of your rotor. You can see here there's a gap. That means the unit was stopped and went to an outage, to make some corrections. And you can see the results were a little better after the outage. You can look at the overall operability of the stator, and you can see why the unit was stopped. The stator operability was going down and down and down, so they made some corrections and improved the overall shape. And if you look at each individual parameter, you can see that all the different parameters that I mentioned during our presentation are here. These are all things that we analyze, and we give a severity reading on those, and you can also trend those values. Okay, at any point you can click here and you can get access to the actual report that was produced that justified the values that you see on the screen. Okay, and if you click on that, you will get access to the report. Okay, so the report is there, so you can have a quick look at why the values are so bad, or why is there a change by looking at the report. Okay, so we'll go into detail on this platform in the Q&A session that will be held on January 21st. All right, now before we go on, are there any questions?
Yes, they are.
There are questions.
There are.
All right, let's go. I'll give you the
Okay, just a sec.
the control.
We have a question from Mark Bisonet. Can we increase availability of hydro machine, hydro generators, or avoid fault outages with this monitoring system?
Obviously. I mean, if you have information that allows you to determine if there's anything serious going on, or if there's anything that's evolving, you are able to determine, first of all, is this something you need to deal with immediately? Is it something that will put the unit in danger in the short term? Or is it something that's evolving that you need to fix for the long run, and that you can intervene at the next outage? You have a major outage that is planned. Let's say you have an issue with rotor pole temperature, or you have an issue with a guide bearing. You are able to put those actions that you need to undertake in your plan, so that you can have the personnel, you can have the parts, you can have the allocation of space, and get all the permits so that you can go in there and fix the issues. One of the best examples also that I know of is that power stations that have multiple units. And I mean, there's a maintenance plan, so I mean, unit 1 is stopped in January, unit number 2 is stopped in July, and so forth. And I've actually witnessed a case in the States where they stopped the unit for maintenance. And while they were doing that, an adjacent unit had a major failure. So now they had 2 units that were down. The information that a system like this can give you allows you to make decisions or make assessments. Whereas, well, we have 4 units. Unit 3 is next in line to be stopped. Well, unit 4 is a mess. So why don't we just keep running number 3 and focus our efforts on number 4? So these are all decisions that you can make based on information. You know, information is power. The more information you have, the better position you're in to make correct decisions and optimize the operation of your power plant.
And we have another question. This is also from Mark Bissonnette. You base the stator shape and or stator center as critical. On which basis? Which standard?
Well, the standards we use for rotor stator shape are based on CIATI. We have our own, but the basic premise is was originally based on CIATI and also based to some extent on Hydroelectric tolerances. In fact, if you look at the CIATI guidelines, they have a picture of one of our sensors in there. They didn't ask, but it was, you know, publicity. We have our own. I mean, we are by far the most knowledgeable company or group of experts in the world in regards to rotor stator dynamic parameters. So we've developed over, what, 34 years now, tolerances for rotor and stator circularity, concentricity, position, reaction to flux and all the different forces. So our tolerances are based on the other groups, but are mostly our own. And to my knowledge, all the tolerances that I've seen are basically pass or fail. Ours are more a question of assessment. It's not a question of scaring people into repairs. It's a question of giving information to our customers as to how the components are performing and how bad is it.
And we have another question from Srinivasan Manivelan. Excuse me if I don't pronounce it well. I have the same issue with my own last name, actually. From Dubai. Would we be better in the market with older machines? In the Middle East and India, we have many older machines with 10, 5, 20 years of age. What is your suggestion?
In regards to system or in regards to... Did you repeat the question, Paul? The initial question?
Would we be better in the market with older machines? In the Middle East and India, we have many older machines with 10, 5, 20 years of age. What is your suggestion? I mean, could be, what are your comments?
Well, if your units...
Regarding instrumentation and system.
Well, my recommendation would probably be the same, because until you know what the condition is, it's difficult to tell. You know, there are units built in the 80s and 90s that were horrible. But there are quite a few that were fantastic. And it depends on the parameter. For example, if you look at units, I've been lucky in the past where I've gone to power stations. Units were built in the 20s,
Wow.
and the things are tanks. You know, it's
Indestructible.
steel is like 4 times over design. There could be a nuclear bomb, and it would still, you know, be functional. Whereas today, if you look at what the OEMs supply. If they calculate that, you know, we need 2 millimeters of steel, well, guess how much steel you're going to get? It's going to be 2 millimeters, not 2.1. Yeah. It's going to be 2 millimeters. So everything is on the edge. Everything is at the maximum potential of the technology. So they are much more susceptible to problems simply because it is more difficult to make these units this way, whereas everything is at the limit. So it's very easy to make a mistake and have an issue. So it's important to have a good monitoring system to be able to determine how well the unit is performing. Because, I mean, we talk about problems and issues, and most of these are usually, if detected prematurely, are fixable. I mean, the OEM's on site during commissioning, and you spot different issues, and they can fix these. In most cases, they do. Sometimes they can't, but in most cases, they do. So we're not saying all the machines are bad, but what I'm saying is that if you don't have a monitoring system, you don't know. And if I were a utility, I'd like to know during warranty period instead of knowing 5 years down the line. Now, if you're talking about 10-year-old, 20-year-old units, as we mentioned previously in other Q&A sessions, a lot of the units that are designed for baseline operation are now called upon to operate as peak load units. So they're cycled much more frequently, and the units were not designed for that. And since the unit were running for quite a few years as base loads, especially the insulation has had damage because of the operation of the unit. Now, if you start cycling these units, most experts expect failures prematurely because of this change in operating condition. So for new units, I would put monitoring system to make sure that the units that are delivered, which at the edge of technology, meet the specifications. If I had 10 to 20-year-old units, I would put monitoring to see if these new constraints or these new operating conditions are causing any damage to my unit. And if my units were very, very, very old, you might have a slight different recommendation because the problems, say for structural problems of the core, are not an issue. Rotors possibly. So that, you know, each case is different, but definitely in all cases a monitoring system is required. And any customer who wants some help in that regard can contact us. It'll be our pleasure to make recommendations based on each individual case.
We have another question. This is from previous sessions. What is the criteria for the number of air gap sensors and their locations, both radially and vertically?
That depends on the size. Well, if we disregard the budgetary issues, it depends on the size. If very, very large machines, we will recommend 12. In fact, there's a power station in the United States that have 12 all the way around. And I remember also a power station in Brazil that had 16, 8 at the top and 8 at the bottom. So it's a dimensional issue. If you have a stator that has a diameter, let's say that's more than 12 meters, you'll put 8. If it's more than 16 meters, you'll put 12. It depends on the size. And also, depending on the height, if your unit is, let's say, more than 1.6 or 1.8 meters, we would recommend top and bottom sensors. And in fact, we had a case at the Itaipu power station where the rotors, I believe, were like 3.2 or 3.4 meters. And they suspected that the actual smaller air gap was not neither at the top or at the bottom, it was actually at the middle. They believed that the rotors would actually have a convex shape, and we installed unit sensors at the top, at the middle, and the bottom, and they were absolutely right. All the smallest air gaps were in the middle, so the rotor poles were actually sticking out. So what time is it now?
Oh, well, we are seven minutes past.
Okay,
I think that we can wrap up for today. If there's any other questions coming in, we'll be glad to answer in the next Q&A session. Please don't forget to formulate your questions in the comment section of this channel.
Okay, so if you'd like to contact us with any questions, maybe you'd like to address your questions in private, you can send emails to my department, which is diagnostics@vibrosystem.com. It'll be a pleasure for us to answer any questions you have in regards to the analysis, the behavior of units, whether it's hydroelectric, turbo, also the mining industry. For those who'd like technical questions, performance of acquisition units, temperature ranges of sensors, installation procedures, things like that, please feel free to send an email to the service@vibrosystem.com. They'll take care of any questions you have. And if you have any questions about types of sensors, if you have any questions about pricing, delivery, availability, any question in regards to the commercial aspect, please feel free to send an email to sales@vibrosystem.com, and they'll answer any questions that you have.
Yes, please don't forget to subscribe to your YouTube channel, and don't forget to ring the bell to receive notifications of new content on the channel. Also, don't forget to write your comments or questions at the bottom of the page after the session. We will answer them during the next Q&A session, as André mentioned, which will be held on December 10th, in 6 weeks from now. The videos will remain permanently in our channel, so you can listen to them at any time in the future.
Yep. So remember that those dates, December 10th for the next Q&A session, where we'll cover turbo generators, and remember also January 21st, where we'll go into more detail in regards to the ZOOMWatch platform for all our customers. So thank you all for listening in this morning. I hope it was interesting. Thank you very much, Paul, for
Thank you,
your
André.
logistics.
Very
And
interesting.
Please be safe, and we'll see you at the next Q&A session. Thank you.
Thank you very much. Hasta la próxima.
Bye-bye.